Okay, so we're switching to crayons, so hopefully those will erase easier. All right, anyway, so we have at the bottom of page 28, we have a new power series. And it's given by, sorry that this isn't so neat. This. Sorry, that crayon doesn't write very well. And it asks us for what values of x does this power series converge. So let's think about this. We're trying to figure out when something converges, so we want to think about all the tests that we know. I know I say in the packet we can use ratio tests, but let's talk about why. Well, if we're going to try to do this for any power series where there's an x in it, we're probably not going to be able to use one of the sort of specialized tests like alternating or geometric or p-series, because those are very specific cases and none of them would really be satisfied by, well, alternating might be, but geometric or p-series, like these have x's in them, they're sort of somehow different, so those tests aren't going to be helpful for us. And then same with like the comparison tests. Sorry, that's really messy. How are you going to know what to compare it to if you don't already know which series sort of converge or not, right? When we have a direct comparison or limit comparison test, it's usually because our series looks a lot like another series that we know whether it converges or not. Well, with these power series, it's not going to be a matter of does it converge or not. It's going to be a matter of where does it converge. So comparison is not going to really help us either. Integral test, I think we can safely say we're going to not want to integrate things where there's x's and n's. Let's see, I'm forgetting tests. You're probably yelling them out to me and I can't hear you. Okay, anyway, so let's cut to the chase because my brain's in a fog. So ratio test is the test we're going to use all the time for power series to try to decide when they converge or not. And that's because for one, it works well for almost all cases, and there's really only one scenario where it's inconclusive, and we'll talk about how to deal with that inconclusive test anyway. So, and now I'm going to do a couple examples like this, but then I'm also going to defer you to other people's videos where they do more examples, just because why reinvent the wheel. So we're going to look at the limit as n goes to infinity. So I'm literally just doing the ratio test here, and again, I apologize for my handwriting here. I don't really even need to put the -1 to the n-1 in here. We've talked about this in class before, right? Because once I put it in absolute values, it's going to be gone. So I'm going to just do x to the n plus 1, which will be x to the n times x to the 1 over n plus 1 times flip and multiply n over x to the n. Wow, it's amazing how this crayon doesn't write as well as the marker. All right. So the x to the n's cancel, and we're left with the limit as n goes to infinity of x n over n plus 1. Now, the limit is as n goes to infinity. So x is just acting like a coefficient. Right, because n is the thing that is going towards infinity. So you want to think about the n's tending towards infinity. So if you want to do direct substitution, we'd have infinity over infinity. And we could apply L'Hopital's rule. And so L'Hopital's rule would say, okay, take the derivative of the numerator over the derivative of the denominator. The derivative of the numerator with respect to n, because n is the thing going to infinity, the derivative of x times n, where n is like the variable, is just going to be the coefficient x. And in the denominator, the derivative of the denominator, again, where n is the variable, is 1. So you could apply L'Hopital's rule, or you could just think about it in terms of polynomials. This is a first-degree polynomial over a first-degree polynomial, so it goes to the ratio of their leading coefficients. So we get, excuse me, x over 1. Okay, so then notice in this case, oh, I messed up. I shouldn't have written this limit as n goes to infinity again because we just took the limit, sorry. So we get just x over 1. Now, this is different than when we had non-power series, right? At this point with ratio test, we would get some number, and the number would either be less than 1, greater than 1, or equal to 1, and that would then tell us what would happen. So ratio test says if our result, so that's absolute value of x, is less than 1, then the series converges. Oh, it's a little wet there. I'm going to move this. Oh, man. This is so low budget. Okay. Then the series converges absolutely. Right? So if absolute value of x is less than 1, then the series, that's a series, converges absolutely. And I'm saying absolutely here because this is alternating. If the absolute value of x was greater than 1, then the series diverges. And if the absolute value of x equals 1, then we have an inconclusive result. Sorry, this is so messy. All right, so what does this mean? Well, if we're asking the question, remember for question 51 was saying for what values of x does this power series converge, then we see that it definitely converges for values of x whose absolute value is less than 1. But what about the values of absolute value of x equals 1? So what we have to do is check those sort of separately. So I'm running out of space, so I'm going to erase here. Obviously, you keep going, so you have all this written down. And sorry you have to watch me erase, but I don't want to make a new video for this one problem, so you'll just have to bear with me for a second. And I think I better dry it so I can write. Okay. So first of all, let's make sure we understand that absolute value of x less than 1, what values does that mean? Well, by definition, the absolute value of x the absolute value is all one way you can think of it is like it's a distance away from 0. So on the number line, all numbers that have a distance less than 1 away from 0 would be the values between -1 and 1, right? These would all be all values that have an absolute value of 1 or less, with the endpoints not included because of the strictly less than. And so what we're really checking here for where it's inconclusive, where absolute value of x equals 1, those would be these two endpoints. So actually what I've just shaded here is the values, all values of x, where we know the series converges absolutely, and I'm still left to find out if it could possibly converge at these two endpoints. Okay, so how do I know if it's going to converge when x is 1 or -1? So I have to check those two. Because ratio test is inconclusive, I have to check those separately. Now that doesn't mean I have to go take a new test on the whole power series, because I really just know it's for those two very specific values when x is 1 or x is -1. So what we do is we go back to the original series, and everywhere we had an x, so first one I'm going to check is, let's check where x is -1. So rewrite the series, and instead of writing an x right here, I'm writing a 1, -1, sorry. Because I'm checking where x is -1. So this is no longer a power series. This is just a series, right? Because I don't have x's anymore. X is being replaced by -1. So I have to figure out if this series converges or not. And so this is like a brand new problem I could have given you on, last week in class. And you'd have to just know, let's see, how do I decide if this thing converges or not? So before you actually do that, you're probably going to want to just simplify this a little bit. I've got -1 to a power, -1 to a power. So I want to multiply them, and I'll add the exponents. So this is negative 1 to the n plus n, so 2n minus 1. So when I add the exponents, I get 2n minus 1. All right, well, negative 1 to the 2n minus 1, what's that going to be? Well, this thing, 2n minus 1, is always an odd number. How do I know that? Well, because 2 times anything is always going to be even, and if you take an even number and subtract 1, you're going to get an odd number. Okay, why do I care? Well, negative 1 to an odd number, that's not alternating anymore. They're always to an odd power. So negative 1 to an odd number is always going to be negative 1. So this really is just the series negative 1 over n. Well, what do I know about that? Well, it's the harmonic series. It's a p series. I could pull out that negative 1 here if I wanted to, but the bottom line is this thing diverges because it's harmonic. It's a p series. It's a p series where p equals 1. So that tells me that x equals 1 is not in there. So it's like an open circle. It's not part of the values of x that make this. It's not one of the values of x for where the power series converges. All right, let's do the same thing now. We check the other endpoint. Let x equal positive 1. So now I'm replacing x with just 1. So these are not the same base anymore, so I'm not going to combine them that way. But in fact, 1 to the n is just 1. So this really is just the power series negative 1 to the n minus 1 over n. All right, so this is an alternating series. I'll let you do the alternating series test, so you could pause the video or something. And so what you should find is it's a convergent alternating series. If you cared to go all the way, it's conditionally convergent, but all we really care is this thing converges. And so we would include the 1 in that series. So the negative 1's not included, and the 1 is included. So for what values of x does our power series converge? The answer would be on the interval between negative 1 and 1, where we include the 1 but not the negative 1.